at how many years until controlled nuclear fusion? 50. If anyone still gives you that answer today, they are either joking or they know nothing about the technology. They are just like those geniuses back in 1901 who said heavier than air machines could never fly. Soon to be footnotes in history's book of jokes. Because it is 2026, and with all the tech and engineering leaps we have seen lately, we can say this for sure. Optimistically, in 2 to 3 years, magnetic confinement fusion will achieve Q greater than 1 and true ignition. This video will show you exactly why it can happen so soon. For those of you who follow us, you will know we have done a series on controlled nuclear fusion, all 6 parts. To this day, they remain the most systematic, professional, and accessible videos on controlled nuclear fusion online. If you want to be the go-to expert on controlled nuclear fusion in your social circle, watch those videos. If you just want to know why controlled nuclear fusion is coming next year, we will break down what it is for you in this video, as simply as possible. Simply put, it is when atomic nuclei of different elements collide and never part. We all know that matter is made of atoms, which in turn are made of an atomic nucleus and electrons. Protons in the nucleus are positive and like repels like. So why do they stick together to form an atomic nucleus? The answer, the strong force. The strong force is the strongest of the 4 fundamental forces. Yup, the force that makes the 3-body problems droplet indestructible. It is the force that binds quark together to form protons and neutrons. In the nucleus, it is 100 times stronger than the electromagnetic force. Even though EM repulsion tries to keep protons apart, it cannot beat the strong force. Under the strong force, protons and neutrons are tightly pulled together, forming the atomic nucleus. Of course, the strong force is incredibly strong, but its range is tiny, only about the size of a nucleus. This is precisely why the atomic nuclei of different atoms can stay far apart, peaceful instead of being squeezed into one clump. But here is the question: if we can bring 2 atomic nuclei incredibly close, close enough for the strong force to act, what happens? The strong force pulls them together, and so 2 atomic nuclei become 1. That is nuclear fusion. Nuclear fusion releases immense energy, which primarily comes from the strong nuclear force. Picture this: the strong force itself holds immense energy, an energy that pulls 2 particles together. When another atomic nucleus joins in, more particles cluster together. They share some of the strong force, and as a result, some energy is conserved. Any system will naturally settle into its lowest energy state. Therefore, this saved energy is released, and that is the source of energy in nuclear fusion. Macroscopically, according to Einstein's mass-energy equation, E equals mc squared, its mass decreases slightly. Let us clarify. Not all atomic nucleus mergers release energy. For all elements, once fusion reaches iron, no more energy is released. For nuclei larger than iron, the nuclear force is less effective. More energy is needed to bind their protons and neutrons. Therefore, fusing atoms larger than iron requires absorbing energy. Nuclear fusion yields vast energy. 5 grams of hydrogen fusion powers an average household for over a century. That is 4.85 million times the energy released from burning all that hydrogen. But making them fuse is incredibly difficult. This is mainly because the strong force has a tiny range. It only kicks in when 2 atomic nuclei get extremely close. And to get them that close, they first have to overcome the repulsive electromagnetic force, which takes huge energy. So far, the hydrogen bomb is humanity's only successful use of fusion energy, harnessing the intense heat and pressure of an atomic blast to fuse deuterium and tritium. But a hydrogen bomb releases energy way too fast, totally unsuitable for peace. Some scientists did propose digging a hole in a mountain, dropping in a hydrogen bomb, and then figuring out how to capture that energy. But still, that is a pretty extreme play. Unless pushed to the brink by an energy crisis, no one would want to go down that road. What we need is controllable nuclear fusion, allowing fusion energy to be released steadily and under control. To achieve controlled nuclear fusion, there are many tech routes. For those who want the details on these, check out our previous videos. Regardless of the tech path, the thinking is the same. It is all about overcoming electromagnetic repulsion to bring atomic nucleus close enough for the strong force to act. So, how do we do it? The answer is to make the atomic nucleus move faster. The faster they move, the more kinetic energy they have, making it more likely to overcome electromagnetic force and collide. And a particle's kinetic energy is directly tied to temperature. Higher T, more Ke. Take DT fusion, for example. Deuterium and tritium are both hydrogen isotopes. Simply put, deuterium is hydrogen with 1 neutron in its nucleus, tritium with 2. Thanks to the neutron, the strong force's reach is a bit wider, making electromagnetic repulsion weaker. This makes their atomic nucleus fusion easier, currently the most viable fusion approach. Scientists found that at over 100 million degrees Celsius, deuterium and tritium nuclei gain enough kinetic energy to fuse. Of course, temperature alone is not enough because higher temps make matter thinner. So we have to find a way to keep the atomic nucleus from scattering, which requires some pressure. So how do we keep the nucleus together? At high temperatures, matter shifts from gas to plasma, meaning electrons completely detach from nuclei. Electrons are negative, nuclei positive, so electromagnetic fields control both. The tokamak is the most common magnetic confinement fusion device. In a tokamak, the toroidal field coil, central solenoid, and poloidal field coil work together to twist out a spiraling magnetic field, confining the plasma. Clearly, a stronger magnetic field creates greater control, allowing for higher plasma pressure, which in turn leads to a higher density. The more plasma packed into a smaller space, the more likely they collide, boosting fusion chances. Besides temperature and pressure, another key parameter is energy confinement time. It is trickier, often misunderstood in science videos. To give you a clearer picture, let us start with a simple example. Think about it. How does a fire keep burning continuously? Obviously, combustion generates heat, and this heat raises the temperature of nearby areas. At such high temperatures, more fuel ignites, allowing the fire to keep burning continuously. Nuclear fusion works much the same way. In a reactor, we use external energy to heat the fusion fuel to a high enough temperature. So under high heat and enough plasma density, some atomic nucleus collide with others. Fusion creates a deuteron with 1 proton and 1 neutron. H2 neutron, helium, Fusion produces a helium atomic nucleus and a neutron, releasing 17.6 MeV of energy. The helium nucleus and neutron carry this kinetic energy. The neutron takes 14.1 megaelectron volts, and the helium nucleus takes 3.5. Since neutrons are uncharged, they are unaffected by magnetic fields and shoot out of the plasma at high speed. But the helium atomic nucleus, being positively charged, can be contained in plasma. If the energy from helium nuclei transfers efficiently to other particles, raising the plasma's temperature, then reaction heat is sustained. In this case, much like a flame that burns on its own heat, the nuclear fusion reaction no longer needs external energy input to sustain its temperature. With enough fuel and density, it can keep reacting on its own. This is called ignition. Reaching this stage means achieving nuclear fusion, ignition. So a crucial factor here is whether the energy from fusion can sustain the high temperatures needed for the reaction. Just like a flame constantly radiates heat, the plasma's energy is also continuously radiated outward. For the plasma, this radiated energy is essentially lost, never to be recovered. If it loses energy too fast, the temperature cannot be maintained, just like how a flame easily dies in strong wind. Therefore, we must maximize energy confinement within the reaction environment. This factor is called the energy confinement time. Clearly, the longer the energy confinement time, the easier it is to maintain reaction temperature for ignition. Temperature, density, energy confinement time, the product of these three is the triple product. Decades ago, scientists already knew from theoretical calculations that once the triple product hits a certain value, fusion ignition is certain. For any experimental device, we only need to know these three parameters to determine if fusion ignition is possible. Moreover, these three numbers can be extended to engineering applications. Take the magnetic confinement fusion device, the tokamak, for example. The larger it is, the longer the... This makes perfect sense. After all, the larger the confined plasma, the harder it is for energy to leak out from the inside. So, tokamak radius, plasma donut thickness, and magnetic field strength, these specs directly determine the fusion triple product. This means how big a tokamak device needs to be built. The configuration and magnetic field strength are decided at design, determining if a reactor can truly ignite. Just like a rocket's design dictates whether it can reach the moon from the very start. So nuclear fusion is not like time travel or making a droplet. Things with shaky theories, it is something theoretically proven, achievable long ago. Like the moon landing, it is an engineering problem. All we are doing is using engineering progress to get closer to that goal. It is not the distant dream it once seemed. In that case, why do not we just build a massive enough device and achieve fusion ignition in one go? Why has it dragged on for so long? Actually, this question, applied to the moon landing, would be like asking, if that is so, why do not we just build a giant rocket and go this year? One bite at a time. The China manned moon landing program needs to build engineering experience step by step with manned spaceflight, space station, and lunar probes. The same goes for nuclear fusion, requiring decades of exploration, accumulating engineering experience bit by bit on smaller, immature devices, then building the final machine once all is ready. In both nuclear fusion and moon landing technology, China has come from behind largely thanks to the engineering prowess of its industry. From large-scale projects. Alright, back to nuclear fusion. Engineering problems cannot be solved in one go, but with step-by-step work, there is always a roadmap. Just like we will likely achieve a moon landing by 2030, the same goes for nuclear fusion. If someone told you now a moon landing always 50 years away, would not you laugh? So with that, let us explore nuclear fusion's recent engineering advancements and its future timeline. First, we will review recent progress. If you follow nuclear fusion developments, you will notice news of a major breakthrough popping up every other day. But after a while, they seem to go quiet again. So among all this news, which claims represent real tangible breakthroughs? First, in December 2021, China's East achieved 1056 seconds of stable plasma operation at 70 million degrees. So what does this mean? First, it is important to stress that East is not a true fusion reactor. This device's main goal is plasma control research. Its design parameters are set so it cannot meet the conditions for fusion. So, whenever you hear news about EAST, you will know its breakthroughs are all about plasma control. There will be no fusion ignition breakthroughs. So, what does steady-state plasma operation for 1056 seconds mean? As we have said, making fusion fuel react means magnetically confining it in a tokamak's donut-shaped cage, which is incredibly difficult. Why is it so hard? We have covered that in a previous video, so we will not go into detail. If you are curious, check out that episode. In short, the plasma dissipates easily. If it does, fusion stops, of course. So we need constant experiments, tech improvements to extend this time. This 1056 seconds refers to how long we can keep the fuel confined in the magnetic field without it dispersing, nearly 20 minutes. So, if fusion happens, it can be sustained for at least that long. It is important to note this is not the energy confinement time. Many confuse it. Think of a campfire. It is simple. Energy confinement time is the time it takes for burning energy to escape. That is too short. It will not light at all, or if it does, it goes out fast, like trying to light a candle in wind. Meanwhile, steady-state plasma operation or plasma discharge time refers to how long the firewood pile burns. The next few news bits about EAST follow this pattern. EAST now sustains steady plasma operation at 100 million degrees for over 1,000. EAST's latest, in January 2026, it demonstrated a density-free regime. So what does this mean? Back in the 1980s, scientists worldwide hit a snag. The plasma density inside a tokamak could not be increased indefinitely, it seemed. Beyond a certain point, the plasma becomes hard to control and very prone to disruption. Then, an American scientist named Martin Greenwald looked into data from various labs and summarized his findings. He found that plasma density seemed to have a subtle upper limit, exceed it, and the plasma would easily break down. This is the Greenwald density limit. Not great news, as it means density. One of the triple product factors has hit a hard ceiling. The good news is, this limit is not a theoretical calculation. It is just an empirical rule, like how all swans were thought white, meaning it is not impossible to break. So, after 2010, French scientists proposed the density-free regime theory. The idea is that, with certain techniques, we can break through this limit and enter the free zone. EAST's experiments proved this, operating stably at 1.6 times the density limit. This means there is still plenty of room to boost plasma density, making ignition much easier. Besides EAST, China's HL3 also completed dual 100 million degree operation last March. What is dual 100 million degree? Plasma contains electrons and atomic nuclei. These nuclei were heated to 117 million degrees. Heating the atomic nucleus to 117 million degrees, nearing fusion conditions. However, the plasma used in EAST and HL3 right now is just hydrogen or pure deuterium. So all experiments are just heating these non-fusing materials to gain valuable experience. For real experiments, new facilities must be built or existing ones upgraded. Besides that, China also has commercial companies working on nuclear fusion with some good progress too. Next, let us look at the progress abroad. The biggest breakthrough was America's National Ignition Facility, achieving self-sustaining ignition last April, with a Q value of around. So 1 part energy in, 4 parts energy out. That made headlines everywhere last year. But why did things go quiet so quickly after that? That is because NIF's approach is inertial confinement fusion, specifically the laser route, where lasers bombard these tiny targets. The target pellet holds DT fuel using laser blast energy to ignite nuclear fusion, like an A-bomb lighting H-bomb. Exactly. Inertial confinement fusion via lasers is essentially using laser pulses to detonate tiny hydrogen bombs. So the energy transfer process goes like this. First, electricity powers the laser, then the laser triggers nuclear fusion. The Q value is the ratio of energy output from nuclear fusion to the laser input energy. So while it seems like positive gain has been achieved, the energy conversion from electricity to laser is way too low, single digit. So we are still a long way from any real net positive gain. This nominal ignition offers little practical significance. Of course, that is not to say this breakthrough is not noteworthy. After all, NIF is the only one in the world to do this yet. Meanwhile, Germany's Stellarator W7X has also made progress. The Stellarator is another magnetic confinement path. It solely uses a set of twisted coils to create a helical field said to be stabler. By 2025, they proved its confinement capability was nearing that of mainstream tokamak. Now that we have covered the recent tech advances, let us talk about the future timeline. As mentioned, none of the currently operating devices worldwide can achieve true fusion ignition on their own. So why did we state with such confidence at the start of the video that ignition is just years away? That is because several ignition-capable devices are under construction. Once they are built and operational, fusion ignition will dawn. First up is China's BEST, full name, Burning Plasma Experimental Superconducting Tokamak. Pay attention to burning plasma. The word burning is right in its name, so from day one it was built specifically for fusion experiments. As mentioned, a fusion device's initial parameters determine if it can achieve fusion, and if its triple product can meet the ignition threshold. BEST is larger than EAST, using a more advanced compact design with stronger magnetic fields to boost plasma density. Its design Q value exceeds 1. Meaning it will output more energy than it inputs once running. But considering all the energy lost from heating plasma for fusion to generating electricity, a Q value greater than 1 is simply not enough. BEST aims for a Q value of 5. Remarkably, it is progressing rapidly and is slated for completion by the end of 2027. So optimistically, in about 2 years, we could hear about ignition. By 2030, we will witness the first light powered by fusion. Of course, BEST's significance is not just about lighting the first bulb with fusion. It must test many unresolved tech issues. As mentioned, devices like EAST and HL3 cannot perform actual combustion experiments. Europe's JET did conduct a few combustion tests, but it lacks superconducting coils. The coils overheat within seconds, so each burn can only last for a couple of seconds. So, it is unlikely they could test the problems of long-duration burning. Those are left for BEST to tackle. Like neutron irradiation, we know that neutrons carry away most of the energy from deuterium fusion. These neutrons are incredibly fast, slamming into the reactor's inner walls with immense energy. The key to deuterium, tritium fusion power is how to capture these neutrons and use their energy. Simply put, the neutron heats it up, that heat boils water, and the steam then generates power. So high-energy neutrons constantly bombard the tokamak's inner walls. Most materials will not hold up. BEST uses an all-tungsten structure, but is tungsten really the best choice? Not sure. We do not know. No one's experimented with such a high-energy neutron source. Further tests await best ignition. There is the tritium breeding issue. Tritium is radioactive with a half-life of just over a decade. This means if you have 1 kilogram of tritium, half will be gone in years. So there is practically no xenon on Earth. But nuclear fusion reactions need tons of tritium as fuel. So what now? We make it a lithium-6 nucleus when hit by a neutron becomes tritium and helium-4. Just add lithium-6 to the blanket, Li. But that alone is not enough because not all neutrons will collide with the lithium-6 atomic nucleus. So if one neutron makes one tritium, the cycle runs out. That is why we also need a neutron multiplier. When hit by neutrons, beryllium and lead both produce more neutrons. Add them in, and you will not run out of xenon. This is tritium breeding. BEST will also test these concepts under real tokamak conditions. In short, BEST will likely be the first device to achieve steady-state nuclear fusion, validating many issues previously beyond experimental reach. Additionally, HL3 will also be upgraded by 2027 to meet fusion burning standards. So HL3 will likely kick off fusion experiments in 2027 as well. Next up should be the ever-delayed ITER project. As fusion followers know, ITER is the largest project ever, a collaboration of Europe, the US, China, Russia, Japan, and South Korea, and India working together to design and build it. It is all about achieving fusion ignition. Our 2021 video mentioned ITER's 2025 completion. It is 2026. It is still under construction. Completion date? Still, considering the state of our global village these past few years, the project's still moving forward at all. Of course, China cannot put all its eggs in one basket. So, beyond ITER, China also has its own China Fusion Engineering Demonstration Reactor. Construction slated for 2027. This fusion reactor goes beyond ITER, targeting commercial power generation, meaning not just fusion but actual electricity. Looks like it will likely beat ITER to the punch, with operations set for 2035 completion. Ultimately, the aim is to see its full commercial deployment by the year 2050. With China's own project, timelines will not be an issue. So, to wrap things up, while no fusion reactors exist on Earth right now, a whole slew of them capable of fusion are on their way and coming very soon. Nuclear fusion is no longer a pipe dream. A clear roadmap is in place. Let us wait and see what happens. Finally, a heads up due to length, some basic concepts in this video were not fully expanded. If any of this was unclear, feel free to check out our previous videos. We are sure you will find answers to all your questions.
This is Neolithic Park. We focus on all science and tech that could shape humanity's future, and aim to reveal the core principles. If you enjoyed this video, please like, comment, and favorite it. If you are interested in aerospace, artificial intelligence data, life sciences, HCI, and the future, follow us. That is all for now.